Section 3.1, it's a long section, right? We've been working in numeration systems, and we'd actually finished that part of it, like proper, as in the numeration systems part. But we were taking a look at the end about what we do when we're working with other bases in general. So they don't have to be, the Babylonians or the Egyptians or whatever, but they're actually looking at what happens when we look at any numerical value for a base. And we had gotten to the slides where we were working on, this is where we left off last time, listing out some of the numerals and then the 2-digit numbers and the 3-digit numbers and so forth in 3 different bases. And we talked about the fact that there's nothing special about these, right? There's nothing special about these numbers. These are some random ones that are chosen to give you an example of how they all kind of work, all right? So the first thing we're going to do is what we did in the other numeration systems is I'm going to start with a number. And we're going to take a look at what would come before it and what would come after it in whatever base system that is. So we're starting out with the number 14, base 5. And we're taking a look at what comes before and what comes after. And just like when we're working with, the Babylonians or the Mayans or the whoever's, usually one of them is just like our system and it looks just like the number that you would have expected. And the other one is the one that takes a little bit more thought in how to figure out what it is. Okay, so basically they're giving us a number. In this case, it's 14, base 5. And it's sort of the middle number. We want to know what number comes before it and what number comes after it. Which one is the simple one that you can tell for sure on this one? Do you know? Is it easy to find the number that comes before? What is it? 13. It's 13. So the number that comes before this one is a very straightforward one. Okay, before 14 is 13. The number comes after is not. Okay, so in our system, in our numbers, if I gave you the number 14, what comes after 14? 15. Okay, so 15 would look like 15. What's the problem with 15 in base 5? Say it, Tessa.
The 5.
The 5. The 5 is the problem. Why is that a problem? Do you remember what I said last time?
Oh, they don't have it.
They don't have it, right? There's no 5s in base 5. So if this had base 6, we'd be fine. There'd be a 15 in base 6, but there's not a 15 in base 5 because there's no 5s in base 5. So when I would normally and naturally run out of numbers in our system is when I get to 9s. So imagine, what happens after we get to 19? Well, I can't change the 9 and make it any bigger, right? So I move one place over, make that number bigger, and I zero out the ones place. Are you tracking with me? Right? After 19 is 20 in our system, right? Well, after 14 in base 5, we've run out of digits. So the 4 becomes a 0, just like our 19 becomes a 0. And the 1 has to increase, so it becomes a 2. And so this number is 20 base 5. Now, I do want you to notice there's a subscript written next to each one of these, right? It's the word 5. There are resources that would use just like the numerical value, like the number 5, and they'd write it in parentheses and they'd make it a subscript. Unfortunately, when you do that, none of us are really perfect in our handwriting. Some of us are better than others. And the problem is that subscript 5 in parentheses might end up creeping up and looking like it's a multiplication number of 5. So it's not ideal. So this is the book's representation, our book, and this is one we're going to use. So you're going to see subscript 5. It's sort of written down lower, right? And it's written in the word form. Okay, so the next one we have is T00 base 12. Hang on. T00 base 12. Any thoughts on which one, the before or the after, is the easier one to recognize here? After. What would come after? Do you know?
T01.
T01, absolutely. Doing the number that comes after in this example is the easier one. I just increase it by 1. There's nothing wrong with changing a 0 to a 1. That's no problem. But going backwards, taking off the number this time is harder because it can't take something away from the 0 at the end, right? It was easy to take away a 1 from my 4 at the end, yeah? But taking away 1 from 0 when there's nothing there is a harder construct. So let me give you another example in our system so you can think about what we do, and then we'll see if we can generalize it to what we do in general for a problem like this. So let's say that we had the number 300, just 300. Now you know what comes before 300. Let's just write it down. What comes before 300? 299. Okay, so let's see what the relationship is between these numbers. Well, the 0 at the end became a 9, right? And because there was another 0, it also became a 9, yes? And the 3 at the beginning decreased by 1 to become a 2. Can you guys see that okay? I'll show you another way to do it too, but I just want you to recognize the pattern first, okay? So if we apply that same pattern recognition to what we have for the t00, the zeros will become, well, they would become the biggest value in this system, but in base 12, the biggest value is not a 9. It's an E. Let me flip back to our screen so you can see. Base 12, we have an E as our biggest value, single digit value. So our zeros turn into the largest place value in that system, which is E's. So there's an E here. And the number at the beginning needs to decrease, right? 3 turned into 2 by 1. So the number at the beginning is a T. T is the number 10 in that system, right? T is 10. What's before T? 9. So this is 9EE. Let me show you another option if you didn't like that one, because you didn't have to like it, that's okay. Let's say that we had our number 300 and we subtracted 1. That's the same thing as going to the number before, right? Okay, so what we do in our system if we're actually doing subtraction is we would say, okay, well, I can't do 0 minus 1, I need to borrow, or I need to regroup something so that I can actually have something big enough to subtract, right? And the problem is that if I go one place value over, there's still a 0 here. That's not going to help me. So I have to go over again, and I have to regroup from here. So my 3 becomes a 2. And when I borrow in base 10, I borrow 10, right? So it's just like what we were doing with the visual imagery of, the Lego blocks. I have these objects, there's 10 of them in there together, and if I break them apart, they break apart into 10 little units, right? So when I borrow in base 10, I borrow 10. So there's 10 here now. But I need one of those to come over again to the other place value, the ones place. So I mark out my 10 and make it a 9. And I borrow to give me a 10 here. This is what we do in our system. You may not write it all out quite this thoroughly, I suppose, but this is what we do. And then we're able to do 10 minus 1 is 9. The 9 minus 0, because there's nothing in the tens place, is 9. And the 2 minus 0 is 2. Okay, that's how we can subtract 1 in our base. So let's look at what it looks like in base 12. So now we have T, 0, 0, and we're subtracting 1. Okay, I still can't take 1 away from 0. So I still have to move over my place values to decrease them. So when I move over to the T is the number 10. And I take 1 away from it, it becomes the number 9. But when I'm regrouping in base 12, all of my long pieces that we were talking about last time have 12 blocks in them. So if you snap them all apart into little bitty bits, you know what I mean, right? There's going to be 12 of them, right? Not 10. So instead of having 10, I'm going to borrow with 12. And I'm going to write it as 12. I'm not going to write it as anything else with T's and E's and W's and stuff like that. I'm just going to write it as 12. We're doing the subtraction, so it's okay. But again, I need to go all the way to the ones place. So I decrease this one by 1, and I have 12 over here. So we're just going to write this down. There's going to be 3 numbers here at the end. They're not going to be exactly what we want right away, but that's okay. 12 minus 1 would be 11, right? 11 minus 0 is another 11. And then my 9 minus 0 is 9. But I can't have a 2-digit number in one place value, right? So when I rewrite this in their number system, I have the 9, that's fine. But for the 11, I have an E, and for the other 11, I have an E. Okay, so that's another way to think about doing this. You can pick, it doesn't matter to me, but those are 2 different sort of perspectives of looking for the number before and after. The other thing that we're going to do is we're going to actually turn numbers from one base into another base. This should feel just like what we were doing with all of our friends, Babylonians and Egyptians and all of them, right? We take one of their numbers, we make it one of our numbers, we take one of our numbers, we make it one of their numbers. It's the same thing, except that there's no, other culture we're talking about. We're just talking about a base system specifically now. So this version right here is going one direction. We're going to take numbers in some other base, so base blank, okay, and we're turning it into base 10. So it says to put the numerals into expanded form. That's step 1. And then step 2 is to multiply out the expanded form. Okay, so let's see how that works. So the first example is 1001 base 2. So I'm going to just write these out with some space so that we can see them a little bit better. Each of them are in a place value. If we were working in base 10, we'd have the ones place, the tens place, the 10 squareds place, the 10 cubes place, and so on, right? That's what base 10 looks like. It's powers of 10. This isn't base 10, it's base what? 2. So instead of powers of 10, it's going to be powers of 2. So this is always the ones place, and this is always the base you're working in 2. And then after that, everything is powers of that base. So this case is 2 squared and 2 cubed, and if we had more, we would keep going to the 4th, 2 to the 5th, 2 to the 6th, and so on. Okay, so this is the expanded form part. This is step 1. Step 2 is we're actually going to write this as a multiplication. So this is 1 times 2 cubed, and 0 times 2 squared, and 0 times 2, and 1 times 1. So can you jump straight from here to here? Yes, you can. If you can make that leap, make that step over, and it makes sense, that's great. If you are struggling to see how you would do that, then do that in between step I did, so that you can see where the places are going. Now, base 2 is really nice because things are either 0, right? Like this one's a 0, and this one's a 0, right? Or they're simply the power of the base that we were in. So the first one is 1 times 2 cubed. Well, that's the same as 2 cubed. What's 2 cubed? It's not 2 times 3, 2 cubed. 8, yeah. So this one's 8. And the last one's 1 times 1. So it's 1. And this is giving me a grand total of 9. Right? I've got the number 9. Okay, so let's do it with the base 12 now. I'm going to write it all out thoroughly, but again, if you don't want to see it, you feel like you don't need it, that's your choice. 10, t is 10, so I'm going to put a 10 in that place value because this is going to be a multiplication fact that's going to follow next. So this is the ones place. I'm in base 12, so the next one's base 12 is the 12's place. And what's the third one? 12 squared. And then each number in that place value is multiplied by the value of the place. So this 10 is multiplied by 12 squared. And then they're not very exciting, but I'm going to write them in. The 0 is multiplied by 12, and the 0 is multiplied by 1. All right, so what is 12 squared?
144.
144. And what's 144 multiplied by 10?
1,440.
1,440. Okay, so if I were you, I would go back to this part of your notes, and I would circle, multiply, highlight, multiply, star, multiply. It's all about multiplication when you're turning from some other base system into our base system. Always about multiplication. But we're going to go the other direction as well. Now we're going to work from our number system, right, base 10, and we're going to turn it into something else. And you'll notice what I'm going to tell you to highlight, circle, star, whatever, is that we're actually seeing the word divide, right? We're going to use division to do this. Everything else is the same. It's just that it's a division process instead of a multiplication process. And it is not at all uncommon for me to have students that just reverse those and accidentally do multiplication. They're supposed to do division or vice versa, right? So that would be my advice to you to make sure you're being careful of. Make sure we're doing division. So here's our number. This is 11,028. And we're going to turn it into a base 4 number. This is going to look like what we did with the Mayans and the Babylonians. Okay, we did them for both of those. What we did is we said, okay, well, what's their place values? So for the Mayans, they were base 60. So we had the ones place, the 60s place, the 60s squareds, and so on. That's not Mayans, that's Babylonians. For the Mayans, it was that modified base 20. So it's the ones place, the 20s place, and it had that weird 360. Do you remember that? 18 times 20. And then we had the 7,200 and 144,000. We multiplied out and we said, this is what these place values are each worth. Well, we're going to do the same thing for whatever place value that we're working with here, and this is base 4. So we've got the ones place, and I'm going to do it right to left because the smallest value is on the right. So the ones place, and then we're doing base 4, so this is the 4's place. And then I have 4 squared, then I have 4 cubed, and 4 to the 4th, and 4 to the 5th. And you might be thinking, well, how do I know how many powers I need? Well, you'll know because we're going to actually figure out what these numbers are. So clearly, the number 4 is just 4, and the number 1 is just 1. But what is 4 squared?
16.
16. 4 cubed? 64. 4 to the 4th. Somebody grab a calculator for us for the rest of these. What is 4 to the power 4? Anybody have a calculator? Jazzy, you have one. Thank you. Can you find out for us? We're trying to get close to this number without going over. That's what we're really trying to do. Okay, we're trying to get close to it. 256. Fantastic. Thank you. We're still nowhere close to 11,000. What is 4 to the 5th? 1,024. Okay, so I need to go higher. So let's do 4 to the 6th, move 4 to the 7th. What's 4 to the 6th? I think it's 4,000 something.
4,096.
4,096. We're getting closer. We're trying to get to 11,000. What's 4 to the 7th?
16,384.
Okay, and in particular, that's too big, right? It's 16,000 and I'm supposed to be stopping at 11,000, so I don't need this last one, right? It is not necessary. I didn't mean for it to erase it, so it's gonna be there. So all of the values beneath it, 4096, 1024, 256, 64, 16, 4, and 1, are all the values that I'm going to divide by in my division scaffold. So remember, division scaffold is the ones that look like the top hats, okay? So we take the number that we were given to start with, which is 11,028. And we're going to divide it by the biggest power of 4 that's smaller, which was our 4,096. Okay, your calculator is going to be necessary for these, at least highly recommended. So how many 4096s, how many whole number of 4096s are there in 11,028? I think it's 2. Is it 2? 2? Yeah, I've got a 2. And then I need to multiply the 2 out here by the 4,096. So what is 2 times 4,096? 8,192, and we subtract. So we need 11,028 minus 8,192. I have 2836. Is that right? Cool. Okay, so we're never going to skip. All right, so 4096, the next one in order is 1024. Okay, so we're going to put 1024 next. How many 1024s are there in 2836? 2. What's 2 times 1024? 2,048. Okay, very good. And if I subtract 2836 minus 2,048, what do I get?
788.
Okay, everybody going good so far? It's okay? Okay, what am I going to divide by next? Yep, 256 is the next one. 256. So how many 256s are there in 788? 3. What is 3 times 256? 768. Ooh, it's almost as big as we wanted, right? So when I subtract, I have 20. And then what will I divide by? 16. No, I need to do 64. Did I skip 64? Okay. So we're going to divide by 64. I know 64 doesn't go into 20. That's okay. We still need to divide by it because this 0 placeholder over here matters. In fact, we saw how much it mattered in some of the other number systems, right? That 0 is a placeholder for us. So 0 times 64 is 0. We still have the same 20 left over we had before. And now we're going to divide by the 16, but that 0 needs to be in there to represent that it went in 0 times. 16 goes in once, so 16, remainder 4. And then I do my 4. My 4 goes in once. It's very tempting to think you're finished, but you're not. I know there's a 0 down here at this point, but we have to divide by every value all the way down to 1. And how many 1s go in? 0, because there's nothing left, right? So we have 2 0 placeholders in this expansion of numbers. So let's see, I have 2, 2, 3, 0, 1, 1, 0, and I'm in base 4. So I write subscript 4. Okay, what do you think? It should feel a lot like what we did before. In some ways, a little bit, I don't know, maybe a little bit more annoying because it goes longer. Typically, these will go longer, like they'll go through more iterations, more subtraction steps and so forth than with the other base systems, but this is what we would get. Notice a couple of things. Every single number that you get out of the division over here better be a number between 0 and 3. It can't be 4 or bigger. Why not?
Because it's base 4.
Because it's base 4, and the only numerals in base 4
0, 1, 2, and 3.
are 0, 1, 2, and 3. So all of these division pieces over here have to be between 0, 1, 2, 3. If they're not, then you've got a mistake somewhere and you need to find it. Okay? Also notice something else that's going to happen, and I'll show it to you again in the next example. This original number we had in base 10 had 5 digits. 11028, right? There's 5 digits, correct? The answer in base 4 has more than 5 digits. Smaller base, more digits. That's going to happen as well. Smaller base, more digits. Okay, let's try one more. This one's 99,999, and we're turning it into base 9 where there are no 9s, right? Got lots of 9s to start with. There's no 9s in base 9. That doesn't mean they all turn into something that's the same, but I'm just wanting to point that out. First thing we have to do is we have to find the powers of 9. Just like on the last one with base 4, we had to find all the powers of 4. So we have the 1s place, the 9s place, 9 squared, 9 cubed. Let's do one more, and then we'll write out the values that we've got, 9 to the 4th. Okay, so 1, of course, is 1, and 9, of course, is 9. 9 squared, you probably know, is 81. After that, you might need a calculator. What is 9 cubed?
729.
That's correct, 729. What is 9 to the 4th?
6,500.
Okay, so that's still not close to 99,000, so we need to keep going, right? Let's do 9 to the 5th and 9 to the 6th and see if we've got them there. What is 9 to the 5th?
59,049.
And 9 to the 6th?
531,449.
Okay, and in particular, that's much too large, right? So this one right here is too big. I'm not going to need that value. But everything less than that, all the values that have powers less than that are going to be division factors. So we're going to start with our 99,999 under our top hat and our 59,049 as our division factor. So how many 59,049s are there in 99,999? 1. And when we subtract, what do we get? Looks like I have 40,009. Yep, 950. Yep, that's what I have too. Cool. Moving our way down, we're going to do 6561. So how many 6,561s are there in 40,950? 6. And what is 6 times 6,561?
39,366.
Fabulous. You guys are doing great. All right, 40,950 minus 39,366. What's my subtraction? What do I get? have 15. Yes, that's what I have as well, 1,584. All right, what am I going to divide by next? 729. So how many 729s are there in 1,584? 2? Okay. What is 2 times 729? 1,458. Wonderful. What do I get when I subtract? So 126? Is that working okay? Okay. And then I divide by 81. So how many 81s? Well, there's only one 81, so we'll subtract 81. Let's see, that leaves me with 45. Is that okay? We'll divide by 9. How many 9s are there in 45? And times 9 is 45. Remainder of 0 doesn't mean we're done because we always have to divide by all the values, including the one at the end. When I divide by the one at the end here, I get 0, and then I'm finished. I promise this number at the end is not always 0. It's just the 2 we did, okay? And then our number that we have is 162150, base 9. Now check it out. Couple things. All of the values that came out of the division over here, 162150, they're all between 0 and 9, right? I should say between 0 and 8. They don't include a 9 is what I meant to say. There's no 9s there. Secondly, the original number in base 10 had how many digits? 99,999. How many digits is it? There are 5. Are you guys tracking with what I'm asking you? Okay, good. There's 5 digits here. How many digits do I have in the base 9 number? 6. Smaller base, more digits. And I didn't actually make mention of it over here, but it's also true over here. Check it out. Base 2. How many digits did I have in base 2 on the first example here? 4. How many digits are there in base 10? 1. Bigger base, base 10, fewer digits. Here as well. This is base 12. There were 3 digits, right? This is a bigger base. Our base 10 number had 4 digits. Smaller base, base 10 now had 4 digits compared to the bigger base 12 had 3. All right? Let me also make one comment. You have to put the subscript there. So the ones that don't have subscripts means that they're in our base. So I didn't have to put them here because these are base 10 numbers, but if that bothers you, you can write 10, like TEN, down there next to it to remind yourself where you're in, which base you're in, and that's okay too.